In this video, I will talk about capacitors and in particular how we can charge them, what happens when we charge a capacitor. So now I'm going to use one of the FET simulations on capacitors, and here this is these two parallel plates. These two represent the capacitor. Now those two, each one of the plates has a wire extending out and this way, but I'm not connecting those wires to anything. I do have a battery. Let's make the potential difference 1.5 volts. I do have a battery. This is the positive side now, this is the negative side, and the potential difference is 1.5 volts. Now what I will do is I will connect this wire to that one, and then essentially I will see what happens. So briefly, you may have noticed it showed an arrow and that the electrons were going to the left here and they were going to the right here. So what I see now, this plate of the capacitor has a positive charge and this plate of the capacitor has a negative charge. Now for this simulation, this process happened extremely fast. It was really fast. And this is true if you make such a circuit where you have a battery, a wire, and another wire here, and you connect the battery directly to the capacitor. Yes, the capacitor will be charged really fast. It will still take some time, but the electrons will move fairly fast and you will charge the capacitor fairly fast. Typically, when we charge a capacitor, we do have some kind of resistor or light bulb in the circuit. But in any case, so now that I saw what happened, I will show you the physics behind this process. So I've done here a similar circuit. I have the battery with the positive side, and this is the capacitor. Now this is the wire, and what I'm showing here is that once you make the connection between the wire that connects the capacitor to the battery, it takes an amount of time on the order of nanoseconds, so that would be 10 to minus 9 seconds. It takes this amount of time for the surface charges to be distributed, for the surface charge distribution to take place, which means once you connect the wires, it takes some nanoseconds, a nanosecond, to see those charges on the surface. Now, once I have those charges on the surface of the wire, I know that this will create an electric field inside, and that electric field will essentially drive the current. Let's look at the directions. Since here I have more positive charge than what I do here, I know that the electric field will point down, and here the electric field will point to the right, and here the electric field will point down, and with the yellow, so these yellow arrows represent the electric field. And because here I have more negative charge on the surface than what I do here, the electric field inside the wire will point up, and here the electric field will point to the left, and here the electric field will point down. Now these arrows represent the electric field, but we know that the electric force can be found by doing Q. If we multiply Q times E, we get electric force. Now I want to think about the electrons, since in most cases these electrons the ones that are moving inside the wire. I want to think about how those will move. Since Q for an electron is a negative number, this means that the force and the electric field will point in opposite directions. So that means here the electric force on the electron will point that way, and the electric force here on the electron will point that way, and the electric force will point up, and the electric force will point up, and then here it will be to the right, and here it will be downwards. Now this is telling me, okay, with blue, so when you see a blue arrow, this represents the electric force. This is showing me how my electrons will move in the wire. So the electrons are gonna start moving this way. This is the electron current. So this is the electron current. Now, since I have some electrons moving this way, and I have the force on my electrons going counterclockwise, I know that the electrons are gonna move that way as well. So this is also the electron current, lowercase I. Now this is what happens if I have, I'm gonna use the red. Since I have electrons flowing this way, if you take a look, once the electrons hit this plate of the capacitor, there is nowhere else for them to go. There is no conducting path that connects the two plates of the capacitor. So if electrons keep moving this way, they will simply start accumulating on this side of the capacitor. And because I have electrons moving away from this plate of the capacitor, they will leave some excess positive charges here. Okay, so these excess positive charges are due to the fact that the electrons are going away. They're moving counterclockwise. Now, this is the charge. These are now the two charged plates of the capacitor. Now we know that eventually this current will stop. We know that eventually the electrons are gonna stop moving. If, for example, you have a light bulb here, you will see after a few seconds that the light bulb is not lighting anymore, which shows you electrons are no longer moving in your wire. Now, so I want to talk about why does the current stop moving? Why do the electrons stop moving eventually and your current goes to zero? Well, if you see here, let's say near the capacitor, I'm gonna talk about what happens near the capacitor. So here I have positive charges, I have negative charges. The capacitor will create, let's use the green one. The capacitor, just outside the capacitor, will create an electric field. The positive plate of the capacitor will create an electric field that points up. The negative plate of the capacitor will create an electric field that goes down. But because the positively charged plate is closer to these points, the capacitor overall will create an electric field that goes up. So with this, I'm showing the electric field. We call this the fringe field created by the capacitor. Now, if you take a look here, the fringe field from the capacitor is pointing in the opposite direction compared to the electric field created by the surface charges on the wire. And let's take a look at what happens here. The negatively charged plate will create an electric field that points up. The positively charged plate will create an electric field that points down, but because this is closer, I will get eventually an electric field. The fringe electric field from the capacitor will point up. Now, if you take a look, the electric field from the surface charges points down, the fringe field from the capacitor points up, electric field from the surface charges points down, the fringe field from the capacitor points up. Eventually, you have enough charges here in the capacitor that they create a fringe field large enough to cancel out with electric field from the surface charges, and eventually you end up getting no electric field, no net electric field in the wire. And if you don't have an electric field inside the wire, that means that there is no longer a current. So And now the time scale, it will take, depending, okay, this is depending on the specific capacitor that you have and the specific wires or light bulb or resistors that you have. This may change, but it will take some time, a few seconds, a few minutes. Again, it depends really on the details of the capacitor, your wires, and so on. From a few seconds to a few minutes and a few hours, depending on the circuit that you have. For the current, for the electric field, the net electric field inside to be zero, and your electron current to be zero. So what I'm saying here is that there are two different time scales. One time scale is the nanosecond, which is the time that the surface charges need in order to be distributed on the surface of the wire, and a few seconds is the other time scale that gives you at the end a net electric field of zero and then zero current flowing in the wire.